Thank you everyone for being here. So this is my presentation on can one use maths and physics to improve sailing. So my first section is on distance and trigonometry. So you can use trigonometry to calculate the distance from point A to point C. So this is an upwind leg. You would go from the start line here and you would try to go to a point B. You can zigzag up, but the point is you have to sail at an alpha or an angle, alpha 1 to point B. You would change directions and tack in sailing terminology, and then make your way towards point C. You can calculate the distance of this using d1a divided by cos alpha 1 plus d1b divided by cos beta 1, as you can see here, the diagram. This is a picture of me having just changed directions or tacked. So this guy is on this point here, and I am on this bit here. You can see how the sail is tightened all the way in to optimize height and to be able to sail closer to the wind, and the fact that I'm using my body weight as a counterbalance against the moment of the wind. So there's another route you can possibly take, which is the green route. So this is clearly longer, but you actually are going at a higher velocity. So you've got to be able to balance whether you go at a shorter distance and you're going slower, or you go at a longer distance but go faster. So which one do you take? Well, I'll get into that in more detail later. So before we be able to tackle that problem, we need to understand the background theory between forces and a principle that you learn in uni called Bernoulli's principle and lift. So about the component forces. Here you have a diagram of an apricot pip, and if you were to squeeze this,
squeezing the pip to the left,
like so, 90 degrees using the such as the red arrows, it's not going to move and it's going to stay stationary. However, if you kind of squeeze it using the green arrows, as the video will surely show, the pip shoots forward because you have a component force causes it to slip forwards. Very important factor to consider is Bernoulli's principle, which is where you have any object which is got a distance on one side longer than on the other, such as a foil, a sail, many other objects. And this is part of fluid dynamics, because you can see you have an upper streamline. It could be air, water, any sort of gas or liquid, and it goes above the top section and also above the bottom section. Because the top section is a greater distance than the bottom section, you can see that it's going to have to go at a faster velocity, because if the fluid is going to go from point A, or this bit here, or the left bit to the right bit of the foil, and reach it at the same time, if it's got a greater distance, because of speed equals distance divided by time, it has to go at a faster velocity to catch up. So because of this higher velocity, the particles are going to be more spread out, and which is going to cause lower pressure. This pressure difference between the bottom and the top is going to cause a lift going from the concave side to convex side. And this lift is extremely beneficial for us sailors, and we use this all the time. There's an equation, which is P minus P naught equals Q naught times 1 minus V squared over V naught squared, where P and P naught and V and V naught are local pressures and velocities respectively, and Q naught is a constant of proportionality. The general thing you need to understand about this equation is that if P minus P naught increases, V divided by V naught will also increase, but then 1 minus V divided by V naught squared will therefore decrease. And this is very important for us sailors to understand, so we know how to use this equation, and this basically sums up what is happening in this model. So you can increase camber as well. So camber results from the asymmetry between two surfaces, such as an airfoil or sail, a wing. So the top section of the wing, in this case, is commonly being much more convex than the bottom side, i.e. positive camber. And the Bernoulli lift forces can be increased by increasing the camber, or the convexity, the depth, the surface area of the wing, achieved by extending the flaps. As you can see, there's a bit of a flap having been extended there, and this increases the convexity and the camber. The flaps, however, add drag in the forward direction, so when the plane is at a maximum cruising altitude, the flaps are retracted back in order to reduce drag, and further lift is no longer required. We can also show how this is applied to sails as well, such as on the next slide. You can note this diagram here, and now on this one is simply rotated 90 degrees. It's exactly the same principle, just different application. So a sail is basically a wing, just rotated, and it's much, much thinner, as you can see. The wind on the outside, on the convex side, has to travel faster, such as in the diagram here, than on the inside, because it's got a greater distance. And because of this, air pressure will be inversely proportional to the velocity squared. There is a lift force perpendicular to the main part of the direction of airflow of the sail. So wherever there's a lift on the sail, it'll be 90 degrees to the average part of the sail, or the average convexity of the sail. Bear in mind, though, that this principle applies to all sorts of fluids, such as water, air, oil, whichever fluid, and that this is very important for sailors. Bear in mind also that the rudder and sail forces act together, such as in that apricot pip, which is very important. In this diagram, or this video, sorry, you can note the very end of the sail, how it slides along the boom or the metal pole. Because it slides, you can increase the surface area of the sail, which therefore will be able to increase. It's basically like extending the flap on a plane, which is very important, and we can change the depth of convexity, which is very important to be able to get more or less lift when going upwind. Okay. So now you can set an angle into the wind as well, which is upwind. And here's a diagram of a keel. You can see the moments involved, where there's a moment caused by the wind, it's a moment caused by the sailors. You can see here that are leaning out of the boat using their body weight, where the moment of the sailor is the weight of the sailor at the center of mass. This varies for different body compositions, multiplied by the height, which is essentially the perpendicular distance. So that's the moment of the sailor. And also bear in mind, there's also a keel side force moment as well, caused by the keel, which is also helping the boat right itself as well. So why would you even bother leaning out the boat? Well, a flat boat is a fast boat, as our sailors say. You can see here, this is a picture of me winning the European Championships in 2018, how my boat is almost pinned flat, and I'm going very fast in very strong winds. And here's a picture of my second day ever in my first ever boat. You can see how keeled over or leaned over my boat is. You can see a little sad face there. I'm not going fast at all. So you can see the difference in how the velocity can be increased and how the boat works much better when the boat is pinned flat. So aerodynamics, which is the forces involved above the water, so involving the air. So you can see that there's a force of the wind in the sail, which is acting in this direction in the green. The red force is the force of the keel due to the water and hiking. And of course, there is going to be a drag force, which is in the same direction as the wind because it's blowing you backwards. So if you add up these forces, you get the FKH and the FWS. They all balance, they cancel each other out. So then you get the force of a drag as a resultant. This is taking you in the opposite direction to where you want to be going. So how is it that a boat moves forward? Well, in order to understand this, you need to take the forces above, which is aerodynamics, as well as the forces below, which is the hydrodynamics. So this is also a book by C.A. Marchai, which was very complicated and was very hard to follow. I went onto a forum and I found that there was a book made in 2010, which is a bit of an update from 1979, but it's made by a guy by Kimball, which was a lot easier for me to understand and be able to explain this to you in this presentation today. There's, of course, YouTube helped me figure this out as well by an account by Howard Sailing, where it's really helped me understand the forces involved. So there's the aerodynamics in a little bit more detail, because it's something I needed to tell you, is that when I said that the lift force generated by the sail is at 90 degrees to the main part of the sail, this varies because you can see how the sail is a bit more curved at the front than at the back. And because of this, the lift force, as a matter of fact, is slightly pushing you forwards, which is very helpful. You can also see how the drag, and you add these up and you get a resultant force, which is the force here. You can also see now this is the hydrodynamics. So cool little video for you to appreciate. This is when I was training in Poland, and I do a flip off the little keel here, which is essentially the thing, or the centerboard, which is stopping you from drifting. And you can understand that this thing here, which is the green green bit here, which is the lift force of the water, you can see that this is generated by the keel and as well the rudder, the little thing that you're steering with at the back. As well, there's the force of the drag. And bear in mind, this is different to aerodynamics because, as a matter of fact, it's not exactly in the direction that you're aiming at, but it's a little bit at an angle. This is because you have to take account drift. So this drag will be at a bit of an angle to the direction that you're pointing at. If you add these two forces, you get this orange net of the water, which is very useful when you add this up to the aerodynamics. So when you add the aerodynamics and the hydrodynamics, you get the red net force here, which is as shown in the direction that you're going upwind. And this force, ladies and gentlemen, is the reason why you're moving forward towards the mark, which is beautiful if you ask me. Now, obviously, we're moving forward in a direction, but sometimes you go fast, sometimes you go slow. What determines this? Well, I'm going to talk to you about the velocity involved. So we get bigger forces if there's more wind, because there's more force in the sail, and therefore you'll require a greater hiking force as well as a greater force on the keel. More hiking force on the keel comes from having more weight and being taller. This is why, unfortunately for me, being tall and heavy is a very, very important factor and advantage to have when you're sailing in a boat, because you can handle more power in the rig. Anyway, I could talk about this ages. It's one of my biggest complaints of the sport. However, I love it and I still make it work. You need very, very strong leg muscles as well as stomach muscles, which is where lots of time dedicated in the gym is crucial, as well on the cycling, on the yoga mats. It's very important. I can't stress this enough. But how do we measure forces and, more importantly, our velocity to make sailing decisions? Well, the key idea, if we know the mass of a boat, the mass of the sailor, and the size of a net resultant force, we can use Newton's first law, F equals ma, to work out the acceleration of the boat. From this, we can also use the law of impulses, Ft times t equals m delta v. I'm sure many of you have heard of these two equations before. Our physics teachers have very well taught us this. It's a bit concerning otherwise if we didn't know this, because it's very important for our exams. It is, as you probably expected, a bit more complicated, but the key idea is this. Now you can see that these formulae are a little bit more spicy, as I like to say. You can see that you got the forces are proportional to the velocity squared, the area of the sail, and the density of the fluid. So because of this, as well, you can see that there is a coefficient of C, which varies on sail size. The bigger your sail, the average is about 4/3, but if you have a bigger sail, you have it a bit more than 4/3. It's a smaller sail, but a little bit less than 4/3. And this is, I'm sure, I haven't seen any personally, but I'm sure there are tables and tables of this for different boats which vary, and you can plug this into the formula here. This will get you a very accurate idea of the force that you'd be getting by the drag of air, the lift of the air. The force can then be used, the force can be explained using Newton's impact theory. So if you multiply the force per particle by the number of particles, you get these lines of math, which is essentially the force of a lift is mass times acceleration, or in calculus notation, the change in velocity times the change in time, times the area times the change in time over change in volume, which is the depth, times density. And then simplifying this, you get the mass times the density times the area times the change in velocity squared. In the physics book I was reading, they summarize this to rho double dash, which is essentially the mass density of their fluid, or in this case, air. And this looks familiar, right? Looks basically the same. So this is how you derive this equation. And it's very important when you receive a set of equations. It's always to understand the full extent of what these equations are saying. You need to know how to derive them. That's how you get the top A-star grades. As well, the same formula applies from other fluids such as water, and other boats, such as you can have keel, rudder, etc. But if we use the mass density of the water and the velocity of the water or boat, u. In the case of lift force, the result is also consistent with Bernoulli's law, where the force arises due to a pressure difference, which is correlated to the square of the velocity difference, as you can see here. Now we have a vector diagram here, which really good represents that the forces that you feel when you're sailing. So the true wind speed, W, hence that capital W in the wind, equals V, apparent wind as viewed by the sailor. Now, this is the wind where have you ever felt that you're running into a wind, and it could be very, very calm winds. You're running and you feel force on your face. That's the apparent wind that you're feeling. And this is very useful when you're sailing, because it changes the direction of the wind, as well as the boat speed relative to water. So this is the speed that you are traveling, i.e. the running sensation. So you can see that W equals V plus U using this vector diagram. And because you can see it's a triangle, you can say that W squared equals U squared plus V squared minus 2UV cos V. And I can show you how you get to this in an appendix if you wish to see it at the end, because I have derived this, of course. But here you can see that U equals the S of V over the square root of 1 plus SV squared minus 2 times SV cos V. So what is S of V, you might ask, because I haven't introduced this to you yet. Speed, this is called the relative speed ratio. And this is defined as the speed that your boat is going, or speed that you are going, all divided by the apparent wind that you feel. So this varies from boat to boat again. I've personally not seen charts of this. However, I do plan on, when I go to university, I'm going to be doing lots of thorough investigation to be able to calculate the speed ratio function of all sorts of different boats, and I'll hopefully make it public to the world. This, I'm sure, will increase the performance of many sailors out there. So this is very, very useful knowledge for a sailor to acquire. And of course, how do you know what wind strength it is? Well, you have charts of this on Google. This is my personal favorite, Wind Guru. I check it every day. So this you can see is on Wednesday, for example, you would see that you had 24 to 32 knots. This is always measured in knots, which 1 knot is 1.5 miles per hour, by the way. And you can see that on the day that you're checking this, it is very accurate. However, as you go further into the future, it becomes more and more inaccurate. So you would just simply have to wait till you become closer to the date, and then you will be able to check it. And lo and behold, it will give you a much more accurate sense. It also gives you of the wind direction and the wind strength, the wave direction, the temperature, all sorts of really relevant information that a sailor might want to know the day they want to go sailing. So as well as that, you have all sorts of practicalities. But however, unfortunately, we can't measure forces while we're sailing, in a race, because it's simply not allowed. But we can do this in professional yacht races, like in the Vendée Globe, where you go around the world, the most prestigious races out there. Typically, the only instruments we have is a racing watch, which tells us how much time has elapsed into a race, how much time we have till the start, a bit like the red, green, go. Essentially, you have 5 minutes before a start, typically, as shown in the picture there. And we also get instruments such as a wind hawk or a wind arrow, which essentially tells us where the wind is coming from. So we know how to steer relative to it, and know that we have to set an angle to it at all times. So these are very useful. But it's not always practical to use theory such as this massive equation here I showed you. It's not, you can't quite do that in your head while you've got trying to concentrate on so many different things, like trying not to crash into people and all sorts of things. But at least you can make rough tactical decisions by looking at the wind speed readings, knowing your speed ratio function before the race starts, when you're on a nice, comfortable desk at home before you go in the water. The velocity of the boat can be estimated by simply looking or observing the distance it takes from the start line in the first 15 seconds or so. We're allowed a racing watch for this. By the time it will have reached its cruising speed, assume constant course direction and constant wind velocity, or speed and direction. For a short period of time, we can also estimate the change in velocity, for example, off the start line, using the law of impulses Ft times c equals m times delta v. So this is now a bunch of decisions that you might need to make while you're sailing. So remember the question where I asked you, well, which course, the blue or the green, gets you to point C first? Which one's better? Well, yeah, it's all about the one which gets you to the mark in the shortest amount of time, because speed equals distance divided by time. You can range it for time as distance divided by speed. Elementary stuff. I'm sure you all know this. But, sometimes you need to know which one gets you there. How do you know which one gets you the time? Sometimes it varies. Sometimes it's the blue that gets you there first. Sometimes it's the green. So there's a bunch of complications that you need to understand to this. And this is where all sailors are always studying this, so we know when to make the best decisions. So these are a bunch of complications: wind shifts, tide, waves, and other boats. So up till now, we've made a model where the wind is at a constant speed and direction. There's no tide or current. The water is flat, so there's no waves. And there's no competitors spoiling things. There's always competitors spoiling things, believe me. Anyway, so you have wind shifts. So wind shift is typically when the wind changes direction. In no sailing race ever has there been the wind staying from one direction. It always changes direction slightly. For example, if you see yourself going on the red course here, and if the wind shifts from northerly to northeasterly, you can see how you'd be now sailing into the wind if you didn't change your steering. So because of this is called being headed, and this is bad. You go slower when you're going close to into the wind. Conversely, if you're sailing the green and the wind shifts from northerly to northeasterly, you can see now that this wind is at a 90-degree angle. You have a lot of power in your sail now, and you're going fast. This is called reaching. I'll talk more about this in more detail later in the presentation. So on the other hand, of course, if the wind goes from northerly to northwesterly, that opposite's true. The green on the left and the red on the right. And you always want to try be on the green tack or the green direction where you're being lifted, which is very important. Another complication is that you have tide and current. This is a whole new force involved when you're sailing, and this makes things a lot more complicated. So in the direction and diagram, you see, there's a cross tide going from right to left. If you took the purple route, the current will push you horizontally away from the windward mark here. You can see you're drifting more and more this way. And you'll still have to tack and sail against the tide in order to reach the windward mark, as well as ending up sailing a much greater distance. However, if you sail on the right-hand side of the course, say on the green, if you think about the forces acting on the boat, you should sail on a slightly bigger angle, so that when you add sideways drift, it's a whole new force. When you add the drag and the current to it, you can see that you'll reach the windward mark without having to tack unnecessarily, such as in red, which is bad. Another thing that you should consider is that when you're in a deep water, there is more tide and current pushing you. So this can be either a very good thing, very bad thing. You can see if the tide is obviously pushing you towards the direction you want to go, you want to be in the deep end. So that is pushing you the most towards the direction you want to go. But if it's pushing against you, you want to go to the shallow, where there's less current, less tide, so that you get less of a force pushing you backwards. And therefore, you get lots of cases of people running aground because people are really trying to get this extreme, especially at a location called Burnham, which is where one of my coaches was once from. So waves, of course, you can see that you can either sail into the waves, such as in this diagram here. Apologies for the volume. You can see here how there are lots of waves and steering, making lots of dramatic steering changes so that I can steer through the waves because they're coming into me. As well as you can see the downwind, where you can use them to surf. Apologies for the music once again. You can see how I'm surfing the wave, and I'm using the wave to go much faster. This is very fun, I must say. Waves, when you're going downwind and larger waves, sailors always look for the route which allows you to spend the most time surfing, because this, therefore, is much faster than not going on a wave at all, because typically the waves go faster than the wind. You can see here that they're changing direction, as shown here. And as well, the waves are characterized by the height, the speed, and the frequency, as well as, of course, the length, where there's an equation omega equals lambda f, as written in the book that I was showing, trying to do this research for, as well as the speed is as well greatest towards the surface of the water, which is therefore represented by this equation. Speed is proportional to e to the power of minus d. This is very important because if you lift the centerboard or the keel upwards slightly, this therefore minimizes the drag and therefore you go faster, as well as it prevents any distortions when you get knocked from left or right from waves. So you can simply use the 3 things you should do when you're using the wave force of the wave behind you, is to make sure that you're always in the front or the top of the wave, so you're surfing downhill, down the wave. It also helps if the wavelength is greater than the boat length, or the wave speed is greater than the boat speed. Avoid wave troughs, so you're not going uphill, as well as water speed is pretty much the bottom of the keel, so you might as well lift the centerboard up. And the final complication there was competitors. Well, one thing I've got to say, it's crucial to be in front of them. Unlike in marathon running, where yes, you want to preserve your energy. In sailing, you want to get ahead as soon as possible. You can see this is the start line between the two orange flags, as you can see. This is a video of me starting near when I was beginning at the UK National Championships in 2021. This boat 216648, that's me. And you can see how all these guys they were all over the line. They were all disqualified from that race because they had a false start. You can see this guy, how he just disappears. And the reason for this is because he's behind me and I'm distorting. You see, I was completely out of the picture now. It's because I was distorting the wind onto his sail, which is called being in dirty air. So if I'm in clean air and someone's in dirty air, I will just simply pull away from them because I can go closer to the wind and go at a faster velocity as well. So one side of the course might be busy and one side might not. Why is that? Well, it could be biased, for example, tide, current, wind being stronger, but you might want to consider, it's really busy there. And if I'm behind them, I might consider going to a slightly less biased side, but still, at least I'll be in clean air, which is a very important factor to consider when you're sailing. So up till now, I've been telling you guys about upwind, which is when you're going towards the wind mark. Here is the trapezoid course, which involves an upwind from point A to C, as I've thoroughly gone through with you guys. Then from point C to point D, which is a reach, I'll explain more in detail. D to E, which is downwind, and E to the finish line, which is a broad reach. I'll cover all these in a minute. This is, of course, you can see a trapezoid course. This is the most common course that I sail in the type of boat I sail. And as you can see here, I've just rounded the mark ahead of at the Polish Nationals at the Nordiska Cup 2021. I was winning this race and I just started going downwind here. Of course, so you can see that usually you can increase the length, such as in Formula 1 of a race course. So you can either go do loops or sausages around AC, so you can go AC, 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 D, E, finish line, as many laps as it takes to increase the duration of the race. Similarly, you can do loops around E and D as well. But of course, this is the most common, but you get other non-standard courses which take place as well, which comes with all sorts of funny shapes and sizes, typically in different types of boats with different types of sails, such as foiling boats or asymmetric spinnakers, all sorts of different funny things, as well as club racing, of course, where they don't have space or the time, or they don't really care about making it a professional race. You can get all sorts of funny courses, which is always fun to sail in as well. Now, downwind is much simpler than upwind, because if you simply ease your sail to 90 degrees, as you can see, it's 90 degrees to the wind. My centerboard is up, the keel, which is the thing that prevents you from drifting upwind. And you can see that the wind is pushing me downwind, or pushing me with it. I'm going in the same direction as the wind, as shown here. And you can also see that there's no moment forces going from port to starboard or left to right, which means I can sit in the boat, kind of relax my legs, which is always fun. And I am now sitting in a boat, and I am now trying to keep the boat flat still without having to really use my body as much of a moment. Now, the wind is going with you. This means that the wind and the apparent wind will act a bit funny to accelerate you, because the faster you go, the harder it is for the wind to accelerate you. As you can see in this video here, you can see I'm going quite slow now, but the wind increases, and all of a sudden, it looks a bit funny. Well, unfortunately, for that, the point being is that the faster I go, the harder it is for the wind to accelerate me, because of the fact that it has to catch up to me first. So it's a bit like running away from the wind. If the wind is trying to chase you, it's got the relative difference between me and the wind is smaller. Therefore, it's going to have less of an effect. So the speed downwind is theoretically limited by this factor of apparent wind. Now, reaching is very similar to this, except it's unlimited speed. The strength of the wind is directly proportional to the boat speed. You can see reaching is when I'm going across the wind from point C to point D. You can see that the sail is about 45 degrees in, and I'm still hiking or using my body weight to counterbalance. This is a picture of me winning when I won the national championships in this class of boat called RS Terra. You can see that I am counterbalancing the boat at the moment to keep the boat flat, and the wind direction is shown by this yellow thing, the wind hawk, and the airflow on the sail is represented by this little squiggly line that I can stick onto my sail called a telltale. This represents or lets me see the airflow, see if my sail is working optimally. And as you can see, it is, because it's running nice and streamlined, and you can see that I've got a nice camber or full use of my sail, which is helping me go fast. Broad reaching, hopefully the video worked, because this is a very cool video. As you can see, I'm going really fast with the spinnaker at the back. And the point is that rather than going downwind and reaching and going, as you can see from point E to finish, you can either go on a reach and downwind to this point here, it's a triangle, or you can just take the hypotenuse, the direct route from point E to the finish. This is much quicker as well. You're still going really quick. And, well, it's a shorter distance. Now, the wind is about 90 to 180 degrees, so about 135 degrees from the direction I'm going. Yeah, I can use a spinnaker here, as well as downwind. I can use spinnakers, but asymmetric, I can also use spinnakers here on a broad reach. And this can even be on starboard or port side. And bear in mind that the forward thrust is quite large due to the relatively large angle with other sails, due to as well, I'm still using my body as a counterbalance to hike the boat flat. Now, foiling. This is my personal favorite part, and this is the future of sailing, and I hopefully want to investigate and I want to use my whole life to be able to investigate this and apply it to super yachts one day. This is my dream, ambition, hopefully be doing it in marine engineering at university as well. So what is a hydrofoil? Well, the whole point of a hydrofoil is to lift the boat above the water, as you can show in this really cool picture of an America's Cup boat. The whole point of this is to reduce drag. Well, drag is only going to slow you down. If you have less surface connected to the boat in the water, you're going to be going much, much quicker. As you can also see, the foil here, because you can see the reason how the boat is lifted. You can see how these wing foils here, the hydrofoils, they lift you because it's got a convex side and concave side. Bernoulli's principle, again, another application of it. And uses this to lift the whole boat out of the water. Now, why lift it out of the water? It reduces drag, and this, because it reduces drag, you go faster, which therefore you generate, because you're running faster into the wind, therefore you generate a faster apparent wind, or that feeling where the wind is blowing into you when you're running in no wind, for example. You feel that wind blowing onto you. If you're going even faster, you'll feel an even greater force. Because of this apparent wind generated, you can use this to sail faster, and then because of apparent wind changes the direction of the sail, or sailing direction as well, you can sail even closer to the distance towards the mark. And this is so cool because you're not only going faster, you're also going shorter distance, which is a completely new course. The red, for example, remember I showed you the blue and the green directions or course routes that take you to the mark. This is a whole new idea, which beats both. So this is going to really drastically improve sailing performance. Now, is it the future? Of course. This is the fastest boat at on the planet right now. It only goes in one direction. That's because it's only got the sails on one side of the boat. And it's got a top speed of 64.78 knots. That is because 1.5 miles an hour is 1 knot. Goes about 90 or more miles an hour. Imagine that on the water. Now, that's even faster than the speed limit. My dad won't even go faster than 60. So you can see this is much faster than any of the other boats around, which aren't foiling. Here's a guy from my club in Poland who was an Olympian, and you can see now how he's using a hydrofoil to lift his windsurf out of the water. And there's also the boat which went around the world the fastest, called the IDEC 3. And this goes at a top speed of 51.3 knots. Not quite as fast as the sail rocket, but because remember, the wind changes direction. Therefore, if you're going to go around the world, you need to have a boat which can go in all different directions compared to the wind, because the wind's not always going to be constant. Therefore, this boat goes around the world the fastest. And of course, you can see it uses hydrofoils to lift itself out of the water. And of course, the future of sport sailing, such as for me, you can see how these things are called a wasp, and it uses hydrofoils to lift above the water. This is, my opinion, the future for the single-handed Olympic Federation, in my opinion. I hope to see it come true. It's very, very impressive boat, and I hope to start sailing in it one day. Just got to save up a bit because they're very cool and pretty expensive. So, in conclusion, I've shown that quite a few things, but trigonometry can be used to sail the shortest distance to a mark. Vector diagrams can be shown to identify the forces of drag and identify resultant forces above and below the water. The sailor can adjust the sail to change shape of the sail and therefore achieve more lift. Centerboards can be lifted to reduce drag. Moments can be used to keep the boat flat and help maximize forces of the keel below the water with forces on this sail above the water. Speed ratio functions, remember the S or V thing? That can be very useful for a sailor to know how to calculate the speed that'd be going or the relative boat speed using true wind speed and different angles. The relationship between speed, distance, time is, of course, very useful for us to use as well. Bernoulli's principle to lift the whole boat out of the water, which is going to lead to a whole future of sailing and more impressive sailing feats, which make you go even faster than 61.4 knots. Eventually, hopefully. As well, a knowledge of wavelengths and waves can help you understand how to handle them when going downwind and upwind. A knowledge of water depths and tides, as well as vectors, and it also can be help with the decisions of which side to go in the course to take. And of course, clever engineering, which is what I'm planning on doing myself, can be helped to make the boat go faster. So in conclusion, we can use physics to improve sailing. And wind, but unfortunately, precise measurements and calculations are not an option, as I said. Wind can shift unexpectedly and the competitors can get in the way, and physical fitness is very much needed. It's an extremely painful sport. Probably the top 10 most painful sports out there, especially for the type of boat I sail called a laser, or Ilka now called. Overall, however, I conclude that a knowledge of physics operates and the boat and above and below the water is extremely helpful. However, experienced sailors may know some of these facts, so you have to find even more nuanced little facts to get the advantage and upper hand on them, as well as rough estimations of the calculations can often be only possible when underwater. So you can't really be doing these calculated things and calculated. It's really hard calculations underwater. You have to do them on land. As well as understanding the key physics principles are very important. And now, of course, it goes to a lot of practice and just spending as much time as possible on the water and in the gym, getting the fitness and the strength going. And this can be the difference between winning a race or not, because in the end, all the top guys know this. It's now down to who can do it better. Hence why it's a sport. So at first, before I conclude and ask you guys for any questions, I'd love to acknowledge Dr. Tan and Mr. Spencer. You've been really great in helping me understand physics and it's real inspiration to me. EPQ teachers, Mr. Kerridge Phipps and Mr. Phillips. My sailing coaches, Kamil Volak, who was my first ever coach ever and who first taught me how to sail in Poland. And then, of course, Mateusz Hanka at the Polish National Sailing Academy when I go on holiday in Poland. The British youth sailing team coaches who are currently working closely with me, James Haddon and Tim Hulse. Team GB RS Terror coach Flynn Davis, who actually first introduced me to the concept that you can use physics in sailing. And this was an eye-opener for me. But I'd especially love to thank the late John Lewis. I wouldn't be here without you, mate. Thank you so much.
Do you want to explain exactly what they are, what they do for the electricity time?
Of course. So here you can see in the red circled on this diagram, these telltales simply they show the sailor on the boat what direction the wind typically is flowing, because the wind has to go on, across, and off the sail in order to be used optimally. Remember, it's the streamline Bernoulli's principle. So these little strings tell us if the wind is flowing over the sail in the way we desire it to go. Sometimes it can be going in an opposite direction, and therefore you have to either tighten your sail, loosen your sail. This is very important for trimming your sail and also for steering. And we use this in all course routes and upwind, downwind, reaching all the time. If anything, I'm looking at these little strings to steer and actually look at the waves, look at that single string. Any other questions, guys? Well, I think that, of course, if a classic boat has already been made, there's a video out there of an Optimist, which is the slowest boat out there. And it is very slow and has been out there since the 1960s. So in the university in Sweden, they've managed to convert it into a foiling boat and it goes fast in 5 knots. There's some really big Swedish university guy sailing a kit for boat for kids, and it goes really fast now. So I'm a strong believer that even though it's an old boat, you can still improve it rather than having to take one from scratch. However, if you're trying to, for example, try get the world record in boat speed, for example, as the Sail Rocket 2 did, you might want to make a new design from scratch. I haven't, but there have been people converting it to laser, and there is actually people who have converted this into a foiling laser. I've never sailed a foiling boat, unfortunately, because I've been solely determined to master the non-foiling boats and hopefully make it into the Olympics one day. However, yeah, they do exist. There are foiling boats for aero. Do you sail by chance? Yeah. Oh yeah, they're great. They're really fun. Yeah, there are foiling boats out there, but this one isn't. But you can buy them probably about $1,000 for a foiling daggerboard, and same with a rudder. Great. Please.
Going at that speed for the full stretch, but presumably that's going to be altered with the number of times you tack and reaching for the centre boards to change the position. Putting up the spinnaker must take some time. How do you factor that into your calculations?
Well, when I do these things, I'm always trying to do it at a period of time where it will not make a difference or a negligible difference to my boat speed. For example, if I do a tack, I always try do it when I'm going down a wave, so that I'm going downhill. So even though I'm going downhill, the sail's flapping when I'm going halfway through, I'm still using the gravity of the wave to go down, which kind of preserves my boat speed. And this is all down to timing. And even Olympians, they still struggle with this. It's a very important, very difficult skill to master. But if you tack going down a wave and you have to get the tunings just right, you can do it and you hardly lose any speed. As well as hoisting a spinnaker, going down a wave, you're surfing the wave, you're going faster than the wind. You can use this time to hoist the spinnaker and then you hardly lose anything. And of course, there will be sometimes, I'm sure you could factor in uncertainties in these equations. However, me personally, I haven't calculated any of these exact numbers yet. However, I'm sure that you could. Please. I not that I've heard of, no, but when I go to university, I will do for sure. Definitely, I'll be the first. Don't copy my ideas, anyone watching the camera. Yes, any other questions? Feel free. No? Yes. Yeah.
Much would you credit an analytical approach to your sailing and thinking about everything you did what you've been able to get? I know you mentioned it's really important to be physically fit and just generally quite adept at handling the boat. Would you say looking at tech analytically really puts you ahead of the curve?
Yeah, for sure. I think that the difference between many sailors out there that want to make it, but you get quite a lot of sailors who are just thinking, oh, it's just a sport. You don't really have to use this thing up here a lot. However, the difference between the men and the boys, if you may say, are those who use this thing called a brain, right? And this is the beauty: brain over brawn, or brawn over brain, or why not use both? So, in my opinion, that if you use physics, clearly you can increase the performance of your boat. It's physically evident. You can see that there's been boats that have been improved using physics. People used camber and the depth to increase the speed of the boat. Yeah, for sure. I take a lot of the credit of my success in sailing. It's been down to my application and trying to use the academic side in physics and maths to try and improve. Yes, Lee?
Complexity or maths control. Would you, and I imagine that use the artificial intelligence to control boats and things could be incredibly interesting to look at. Are you aware of the research doing?
Yeah, you do get, for example, even in driving cars, you get people trying to get these cars which are driving by themselves, right? Elon Musk and all those guys. Yeah, you do get boats which have autopilot. I've used autopilot before on big yachts, Beneteaus. They use autopilot which steer for you through the waves. It's a very important thing because you don't want to stand there steering day and night. Of course, you don't want to tie an umbrella to stop the steering wheel from spinning. You want to try, obviously there are computational technologies which help you use technology so that you can improve your sailing. Of course, so where you get sensors such as sonar charts and sonar readings and all sorts of different electronic devices which can help you improve your sailing performance. Yeah, definitely. Anybody else? Okay. Oh, yes.
Aspect of design where at the moment teams or manufacturers or franchises are particularly looking to obtain a competitive advantage. So it strikes me that there's more emphasis at different periods of time on different pieces of ameliorating different pieces of technology or revolutionizing approaches. Is there emphasis on any particular area now of competitive sailing or not really? It's looking at it more of a mindful gains thing where people are looking to make full incremental improvements all over the place.
Well, I'm sure you can make little improvements in everything. However, part of being an engineer is coming up with new concepts and new ways to improve. You know, there's obviously improving, but there's also completely innovating and coming up with new ideas to improve as well. Yeah, I mean, in my opinion, foiling is the one way how boats can improve the performance. But I mean, I'm sure you can make a boat more streamlined. You can increase the sail size to boat weight ratio, all sorts of different things. I'm sure you can increase lots of different ways how boats can go faster. It's just quite difficult on a large scale because you've got a lot of money invested into it and you don't want it to go wrong. Anyone? Yes.
While you're sailing, of course, you're in the middle of everything and you're aware of apparent wind speed rather than the actual wind speed. Is it important to have a number of people observing from the outside to give you feedback?
Yes. My coach, whenever I have a coach on the motorboat, I always ask to take a little iPhone or camera with him so he can film me. Not only is it good for Instagram, but of course, it's very good to reflect at the end and be able to see, I could be working harder here. My sail isn't quite set up as optimally as it could be here. My steering is off. There's so many little things where you can improve your performance physically, such as steering or hiking or technique in terms of what you yourself are doing. But of course, you can have a few degrees off the wind, and this will be shown in your telltales with little strings, as Aiden might ask about steering relative to the wind. And there, yeah, I'm always trying to have a coach film me so I can always see how to improve visually, because I'm a visual learner, and it's always easiest to do that using technology and evidence that you're not doing. Sometimes you might think your boat is flat, but as a matter of fact, it's 5 degrees off. Sometimes when you're going under a lot of pain in your legs, you're not in the right mindset to see these little tweaks, especially when you're focusing on 10 different things at the same time. But yeah, for sure. I mean, these little videos are the difference, in my opinion, and how you can really spot the differences between the top Olympians and where I am at the moment, and hopefully one day get to that level. So this is going to be my summary presentation on can one use maths and physics to improve sailing. So as an introduction, my 3 motivations. I was motivated to show you, well, 3 passions, sorry. My passion was maths, physics, and sailing. And I'm motivated to show that maths and physics can indeed be used to improve sailing. In particular, for the route taken going upwind, as in sailing at an angle to the wind, as well as how a boat lifts above the water using foiling. I had a few research methods, one of which was Howeff's YouTube channel, a guy called Howef, another called Say Marshai, which was a very complicated book, as well as Kimball, which was a more modern 2010 book. Another was my coaching experience from international level coaching Team GB, as well as photos and videos which I had received from sources of performance. So the first main question was what route to take upwind. There were 2 possible routes. One was shorter one was a longer one. The shorter one was to travel at a slower velocity, but travel shorter distance, and the longer one was a longer route, but to travel a slightly faster velocity. In summary, the way I tackled this was to calculate the trigonometry for distance. I also used vector diagrams for velocity, as well as using the equation speed equals distance over time, so then you can rearrange over time as distance divided by speed. So the journey in particular, so this was like a game of snakes and ladders, to be fair. It was very fun to do because at first I was instantly on a snake because I was going to do an essay. Then me and Dr. Tanner had a discussion where actually the performance was the best idea to do, which I ended up doing now. Straight away, I made some diagrams of PowerPoint for trigonometry and distance, which was great. And after that, I decided, I should probably try calculate the velocity going upwind. So there are two parts to that. The first part was to calculate the forces, which were involved to make a boat go upwind. And this was a bit of a snake because I realized that I was only trying to find the forces above the water, either aerodynamics. And this was essentially based on more online resources I used to calculate this. And I realized that if I only summed up the aerodynamics, the boat actually moved in the opposite direction to where I wanted to go, which was very condescending and kind of scary. So then I realized, I decided to do a bit more digging, and I realized from a guy called Howarth on his YouTube channel, if I sum the forces above and below the water, I can then get a net resultant in terms of above and below the hydro and aerodynamics when the boat shoots forward. This then was how forces worked, but then after that I had to try calculate the velocity. So that consisted of trying to find a speed ratio function, which was essentially a function which, if you know the wind speed as well as the speed ratio function, every boat has one. You can then use an equation to calculate the velocity. As well, after this, that was a huge one because that was really complicated to figure out, but eventually I made it. And after that, I used distance, time equals distance over speed, because I knew the distance from the trigonometry, I knew the speed from doing the velocity, speed ratio function. And after that, I could calculate the time. So the other main question I had was, how do some boats foil and some boats don't? Well, it's the same principle for how a sail uses lift and Bernoulli's principle to move going upwind. It's explained using this equation on the board as well. I explained this in a lot of detail in the actual presentation, as well as the apparent wind was generated. The faster you go, the more apparent wind due to relativity. And eventually, I believe that this is going to be the future of sailing. And I hopefully will divert my life into this and this area of physics. So the journey for the second problem, well, I started off with a lot of online material. There was so much of it, but it wasn't really related to sailing. It was more to pipes and for planes. But I realized, luckily, that planes are the same sort of thing as a sail because it uses wings. And the sail is basically a wing, just rotated 90 degrees. So once I discovered this, I was on my way because I realized, well, if from the book Kimball, which was a book I was reading from in 2010, explained that the force proportional to the area times the velocity squared, i.e. Bernoulli's law. And this, using pressure is forced by area, if I substitute that in, get pressure proportional to velocity squared. This was a concurring with the equation which I showed in the previous slide, if you're looking at the presentation. And after that, I realized that's how I derived it, essentially. So I was feeling really good after this because I'd learned Bernoulli's principle, which was a great thing, as well as how a boat can lift, which was starting my future research into where I wanted to go with my, in my university studies, as well as camber, which is essentially the depth of the sail and how the sailor could use the depth to gain more or less lift, depending on the wind conditions. So after this, so this was my main first plan, was just to cover all this, but I wanted more. So I realized, I could add other wind directions because I only did upwind when you're going at an angle, but I involved going in at 90 degrees across the wind, reaching, as well as downwind when you're going with the wind, the same direction. So this was much easier because I could essentially extend the the course diagram as shown in the slide there, which was very easy to use PowerPoint, a very good interface to use, as well as I was able to say from sailing experience how I could relate all the physics to be able to explain this because I already knew this from my international level coaching. Well, somewhat understand it. Now I could very easily understand it with a better detail so I can present it. As well, I use photos and videos which I had gotten from these trainings, hence why it's a performance. I had to show that I myself was able to do this as well, hence why I try to make it as realistic to a performance as possible. The next thing I decided to do, because I was just loving the whole presentation so much, I decided to make it my project in there. So I decided that I wanted to cover the complications because in a real sailing world, the wind oscillates, changes direction. It also, you have tide, you have waves, and you have other competitors. These are all aspects which you need to consider when you're doing any sort of model to the possible real life complications. So tide And wind shifts and competitors, waves, out of those, in my opinion, waves was by far the hardest to understand because there's an equation which was speed proportional E to the exponential function of the negative D, the distance. This essentially, or E to the minus D, this essentially understood that the deeper you go in the water, how the velocity varies with depth. So you could use this to surf a wave, and also the formula omega is lambda f, which is essentially the distance of wavelength. As well, wind direction was kind of quite a good one to do, so I had to use vector diagrams to understand this as best I could. So, but the rest was kind of easy because I already knew quite a lot of it from my experience. So to reflect and to evaluate, so the project plan was mainly useful because to confirm the due dates, the pace, as well as to send progress to teachers so I could check on whether I'm doing the right thing or not. Afterwards, I would use the research of others as well. This is important to understand. So I would use online, was a bit simple. The Howarth YouTube channel was more for forces. This was really good for that. Marchai, the C.A. Marchai, which is the 1979 book, was basically the Bible. It was huge, this book, 300 pages long. But it was really hard to understand. So I was looking online for if there's a forum for where I could find a simpler book. And I found one called Kimball, made in 2010, a more recent version, where I then could finally understand what they were talking about velocity, because this was a university level investigation. After this, I could do certain things with no research as well, because I had PowerPoint diagrams, I had experience, I had trigonometry, distance ideas from my math classes, as well as pictures and videos I'd gathered over the years, which I could then use to show you guys exactly what I meant. I had to choose the certain pictures and videos which were relevant to the principles. Sometimes I would be sailing in a perfect way, but it doesn't show the real physics concepts, even though a sailor could appreciate it more. I had to show, even though I could be sailing not as well in this picture or video, it could show the physics concept a lot better. It's a lot easier to demonstrate these aspects. So it was quite a fun process. It took a while to do that, but I managed. So in conclusion, my two goals, I reached my two goals, I would say I did show that how to use physics to improve going upwind, as well as how about lifts, which was a very important. These are my two goals originally. As well, on top of this, because that was my original plan, I ended up also covering camber, which was the thing I discussed, other directions, as well as complications. So these are even more things which I set out than what I set out to do originally, which was a great success for me because I did more than I planned. As well, I wanted to do more, but I had the time pressure. I had only 40 minutes, 35 minutes to do this. So if I was to do this next time, I would very much like to do it to include numerical examples, so real numbers involved in that, as well as ice boats, because that's something that's quite cool. You can use boats on rails to go basically sailing on ice, which is a really cool thing, as well as the center of mass of a boat and how it varies between the boats, as well as the different sail shapes, different materials for sails, different weights and shapes of hulls. So these were lots of different things I could add in the future, buoyancy. But the thing is, I will if I had another chance to do this. So this was a really fun presentation project to do. I loved every moment of it, but it was really hard work. But I loved it, and I'm very happy I managed to do it. Thank you, everyone.